This is Bruce Perrin's Kilo 6 Bravo Papa, and let's talk about the counterpoise, the other half of your antenna. This program came about because I couldn't understand how the end-fed half-wave antenna could possibly work. It had this tiny counterpoise, which was 0.05 wavelength, and I couldn't figure out how all the current could come back to that tiny bit. And this led me into a rabbit hole of learning about counterpoises in antennas. And now it's your turn. It turns out the EFHW antenna does work, but the part we call the counterpoise isn't really the counterpoise. We'll get into that later. There are 94 slides, so don't blink. I'll take questions afterwards. AC gets a lot harder than DC electricity. It's a big step to go from DC to AC theory. And a lot of us only have an intuitive understanding of DC electricity, if that. RF is the ultimate AC. We're not going there today, but microwave is the ultimate RF, as shown by this radar PCB. All of the little squiggles are components, and in fact, there are inductors, capacitors, and mixer, all made out of PCB traces. So that shows just how complicated AC theory can get. Today we're going to start really simple. This is as simple as you can get. You can't force current through a one-terminal circuit. This is the fundamental theory of electricity. It has to be a closed loop. Open circuits don't conduct electricity. There must always be two terminals, a current supply, a current return. Without both, no current flows. Then, how does your antenna work? So here's your coax. It's feeding a vertical antenna from the center pin of the coax, and it's connected to a ground rod by the shield of the coax. And what is it between these two things that is returning the current? Because they're not connected. And antennas must always be two-terminal circuits. Current flows from the transmitter to the antenna on the center conductor of the coax. Current must return from the antenna to the transmitter on the shield of the coax to complete the circuit. So what invisible thing completes this circuit? And if all of the current returns to the transmitter, how do we transmit anything? There's a third component connecting the antenna elements, and it's space-time. Hey, we're only in a few slides, and I'm getting spacey already. The two elements of a dipole illustrated here are connected to each other by space-time. So here we have the magnetic field in red, the electric field in blue, and the oscillating antenna current induces fields in space-time. And those oscillating fields induce current in the antenna. So that's how these two halves are connected, even though there's no wire between them. So how is space-time part of the antenna? You can think of space-time as an electronic component that is everywhere. Like a resistor or a capacitor, space-time has well-defined electrical properties that are useful in a circuit. And of course, this is my fantasy of a space-time component. Space-time is everywhere, so you don't have to solder it onto your PCB. Space-time has electrical properties. It has magnetic permeability, the ability to support a magnetic field that's related to inductance. It has electrical permissivity, the ability to support an electric field that's related to capacitance. It has a propagation speed, that's the speed of light. Wavelength comes from this. Wavelength is just space over time. It has an impedance. Space-time has an impedance of 377 ohms. So how do antennas really work? Well, radio waves don't just fly off of the antenna. The antenna creates fields, electrical and magnetic fields. The fields are in space-time. The two wires of a dipole and space-time and the transmitter and the feed line form a complete circuit. Current returns to the transmitter. So what do the fields do? Just as a moving magnet can induce an electric current in a wire, changing magnetic fields induce electrical fields in space-time, and vice versa. The oscillating electric and magnetic fields sustain each other and can propagate over a great distance. That's what radio waves are. It's just these self-sustaining fields that keep each other going. We're going to talk about why some antennas aren't so good. A compromise antenna is always better than no antenna. But maybe it's not the best antenna you could have. You might make a better compromise if you understood antennas better, did more work, etc. Most ham antennas are too small, too low height to avoid ground loss, not matched to the frequency, have wires too thin, have a bad counterpoise, etc. These are the ways we counterpoise. But compromises get you on the air. Waiting forever for the perfect antenna doesn't. You'll always hear from people who won contests with compromise antennas, so they must be good, right? There's varying theoretical knowledge and use of modeling and measuring procedures among antenna manufacturers. Some of them are really good. Some only do A/B testing, which can lead to self-deception and deceiving the customer unintentionally because there are just too many variables. And we'll talk about how to do measurement better. So what's a counterpoise? The part of an unbalanced antenna that returns current to the transmitter. This quarter wave vertical is a very common unbalanced antenna. It has a vertical element and counterpoise radial elements. It is unbalanced because the two parts are not the same. Well, what's a balanced antenna? A balanced antenna has equal elements, often wires, for each side of the circuit. This horizontal dipole has two equal wires, so it's balanced. The two wires are in a circuit with space-time and the transmitter and feed line. Here's a loop antenna. A loop is a balanced antenna made of one wire with both sides connected to the feed line, so it more intuitively makes a circuit, and it returns current to the transmitter. Although it makes a circuit on its own, the loop is still in a circuit with space-time, and you can see all of the fields that antenna is making. There are balanced feed lines too. So coax is unbalanced. Ladder line is balanced. We often use a balanced to unbalanced transformer to go from unbalanced feed line like coax to a balanced antenna. Verticals and random wire are two examples of an unbalanced antenna. We'll get into the end-fed later. The radiating element in the counterpoise, the part that returns the current to the transmitter, are physically different in an unbalanced antenna. Unbalanced antennas can be modeled as dipoles with unequal parts. It's the unbalanced antennas that often skimp on the counterpoise. And there are a lot of misconceptions about the counterpoise. People say the counterpoise isn't important because it is not the radiating element. That's false. The counterpoise is necessary to return current to the transmitter. All of the current must be returned. None flows without returning. The antenna will work poorly unless the current is returned efficiently. More misconceptions. You only need 0.05% of the wavelength for the counterpoise. That's often stated for the end-fed half-wave antenna. That's false. The 0.05% wire on an end-fed is not the main counterpoise. The long section, because it's most of a half-wave long, returns its own current. It's both halves of a dipole. So let's talk about the importance of measuring antennas accurately. Hams have historically been very poorly equipped to measure their own antennas. We only had really indirect methods like the S-meter, the thickness, the thickness of our QSL pile, and SWR doesn't actually measure antenna performance. If anyone tells you an antenna with a great SWR is an optimum antenna, it's working well, no, that's not true. What's the effect of the lack of accurate measurement? Because antennas were so difficult to measure, craft knowledge took the place of science. And there's been a lot of confusion and misconception about antennas. That continues today. But today we have a new method to measure antennas accurately. Let's talk about how we've been doing it and how we should do it. So what do we measure? The fields emitted by an antenna are separated into the near field and the far field. The near field is the electric and magnetic field close to the antenna. These fields actually return significant current to the antenna, so this is also called the reactive field. The far field is farther from the antenna, and the far field behaves as plane waves and better represents what happens at a much greater distance from the antenna. And the far field is also called the radiative field. To understand antenna performance, we must measure the far field. So here's the best I could get of a picture of the near field and the far field. The field shapes are not mathematically accurate. If you're an electrical engineer, you want to know where the pointing vectors are. I didn't include them. So this is showing close to the antenna the fields that actually return current to the antenna, and farther away from the antenna, the self-reinforcing fields that radiate to a great distance. So how do we measure antennas? The best way to do it so far has been an antenna measuring range. And for HF, it's a huge, flat, empty plot of land with the antenna in the middle and a moving tower at a distance from which far field signal strength can be measured at various horizontal and vertical angles to the antenna, and thus we can determine the antenna pattern. Now, you can already figure out why your antenna manufacturer doesn't use this, because they can't afford a huge, flat, empty plot of land. At least most of them can't. At UHF, however, it's practical to do this in your backyard. At HF, it needs lots of acreage, and moving the tower for the measuring antenna can be very elaborate. So this method can be very accurate, and it eliminates the variables in some other methods, but it's not practical for most hams. This is a antenna measuring range. This is for far UHF or microwave. It's an RF anechoic chamber, And the measuring antenna is to the left of center. It's log periodic to measure a broad frequency range. The device under test and its antenna can be rotated to measure the antenna pattern, and that's at the right. How do we measure antennas? A/B testing is another way. Compare two antennas with the cooperation of a distant station. Whisper or the reverse beacon network can help to automate this process. The advantages are this uses the equipment you already have. The problems are there's still too many variables to give a good answer. For example, propagation changes over time, fading from moment to moment, so it's easy to deceive yourself. Self-deception is something we should talk about. It's the phenomenon of your car running better after it's been through the car wash. What actually happens is you like your car better that way. You want your antenna to be good, so it's easy to deceive yourself when using poor methods of measurement. Good scientific methods of measurement protect you from self-deception. So how else do we measure antennas? SWR indicates the reflected power at the transmitter. The advantage of this is it uses the equipment you already have. It's very easy to do. The disadvantage is that SWR is not a measure of the antenna radiation at all. Zero, nada, it isn't. So you're deceiving yourself, and we'll discuss why. How else do we measure antennas? Theoretical modeling. So this is using NEC or its various derivatives. A mathematical model of a real-life phenomenon. The advantages of that are it can be done before the antenna is built. It's easy to change and retry, and it tells us a lot. It uses the computer you already have. It doesn't need an antenna measuring range. The problem is learning the program and entering data takes lots of time. The program misses real-world issues, so you can still deceive yourself. So here's the future of antenna measurement. It's airborne. Drones are the solution. Programming a drone to fly to many points on a flattened hemisphere around your antenna and sampling the signal strength at each point is within the reach of hams today. With drones, we aren't guessing any longer. You should still model before building your antenna. So here's a commercial antenna testing drone. This is for frequencies we're not interested in. There are issues that we have to solve in using a drone for measurement. One is making a sampling antenna that works through a 90-degree change in angle, because we're going to measure 400 feet straight up and we're going to measure maybe 1,000 feet to one side. And maybe that means adding a servo to turn the sampling antenna. We need to manage electrical noise from the drone and the environment. We need to consider RFI to the drone, so use low power. We need to consider reflection from the environment, but this is a real-world part of your antenna performance. And be aware of neighbors and regulation and the risk of losing the drone. The only accurate antenna measurement is radiated field strength at a distance, measuring the far field at many points to determine the antenna pattern. You only get this with a drone or a ridiculously expensive measuring range. Consider it like putting a thermometer in the refrigerator versus just going by how the food tastes. The goal is the food, but the thermometer helps you understand how you're getting there. So Let's talk about radiation from your antenna and loss. Some of the power that goes to your antenna ends up as radiation, in other words, radio waves. This is the useful part. The rest ends up as loss. This becomes heat, although you probably never notice the heat. Where does loss come from? Mainly the ground. In an unbalanced antenna, so say a vertical antenna, the ground is almost always the main path for current return to the transmitter. And the soil has resistance, and it's part of the circuit, so power is lost there. A balanced antenna at a practical height for most hams will also radiate into the ground. So power is lost that way too. Let's talk about dipole height and loss. Most of our dipoles are way too low because we can't afford huge towers for them. A dipole 1/4 wavelength from the ground or less has the ground as a lossy reflecting element. It could be considered a two-element beam pointing straight up, thus a sky heater. And you can see it's a decent NVIS antenna for contacting closer stations. Adding multiple parallel ground radials under that dipole would reduce the loss and make it a good NVIS antenna, but it would still mainly radiate straight up. Half wave high is better if NVIS isn't your goal. The higher you can get it, the more like a theoretical dipole it will perform. Let's talk about the kinds of loss in your antenna. Ground losses dominate. This varies with each installation, but 36 ohms resistance in returning current to the antenna isn't unusual. And for a quarter wave vertical, that's half the power. Half the power isn't even getting out of the antenna. Electrically short antennas are very lossy. The effective radiated power diminishes approximately with the square of the ratio of the element's electrical length to 1/4 wave, no matter how well you load it with your tuner. So a half-size antenna is 1/4 as effective. That's for dipoles and verticals. For loops, a half-size antenna is 1/16 as effective. The kinds of loss in your antenna are resistance losses because the wire or antenna element isn't a perfect conductor, and this is made worse by the skin effect because only the skin of the wire carries RF, not its whole diameter. So let's say we're working 10 meters, we have 100 feet of wire. 24 AWG would have 20 ohms resistance. That's pretty lossy. 12 AWG, a thicker wire, would have 5 ohms resistance. In contrast, the DC resistance of these wires is much, much lower and would be a fraction of an ohm. So the skin effect drastically increases the resistance of wires when they carry RF, including your antenna wires. We also have dielectric loss, which is complex. There's several different ways it happens. It's a loss in the insulating portion of your feed line. We have transformer loss because we generally have a balun feeding these antennas. Ground loss almost always dominates. So let's measure radiation and loss. An antenna has radiation resistance, the effective resistance that comes from the work of radiating radio waves. So we actually measure the efficiency of an antenna as resistance. The antenna also has loss resistance, the resistance that comes from all of the losses in your antenna system that make heat rather than do real work. So again, radiation resistance, loss resistance. The loss resistance is often larger than the radiation resistance. So here's a graph of a quarter wave vertical and a short mobile whip versus ground loss. So on the bottom we have ground resistance, and as the ground resistance gets higher, you can see the efficiency is now dipping below 20%. And let's look at power distribution for a quarter wave vertical. So here, if we have no ground resistance at the left, we're 100% efficient. And the dotted line is heat loss. So we have no heat loss at the left. Now, as the ground loss resistance gets to 36 ohms, those two lines cross. So at 36 ohms, half of the power is going to heat, half of the power is going to be radiated. As the ground loss increases, we get down close to 20% efficiency again. So how do we measure radiation and loss? We generally do it through theoretical modeling, but we can derive it from accurate field strength measurements. And so here's our antenna on the right. The antenna can be looked at as two resistors, the radiation resistance and the loss resistance. And you can see the efficiency equation in the bottom right. So here's a real antenna circuit, and we're going to explain here why SWR does not tell you what's happening. So say this antenna has 36 ohms radiation resistance and 36 ohms loss resistance. So it's a vertical with a poor radial system. And we may get perfect SWR out of this antenna because it's still showing us the impedance that we expect to see, even though half of the power is going to heat the ground. So this is why SWR lies. SWR does not distinguish between coupling to the radiation resistance and coupling to the loss resistance. So say you have a very lossy antenna. Well, that may have perfect SWR because you're coupling to the loss. And when you have antennas that are flat across the whole band, you start to get suspicious. You know, that's not how a real antenna performs. So am I coupling to the loss more than I am coupling to the radiation resistance of the antenna? So with a fixed antenna, the flatter the SWR is over a wide band, the more suspicion that you're mainly matching the loss. And here's the best example. A 52 ohm RF resistor is likely to have a perfect one-to-one SWR and not radiate much. I know there's somebody out there who hasn't worked all states on a light bulb. Impedance matching is important. It's just not radiation measurement. So this is why we need the counterpoise. We've been talking about the ground resistance and the loss of the ground and how we're just turning our power into heat. And the counterpoise helps us to reduce the ground loss the resistance of the soil in returning current by replacing the soil with a more conductive wire. Reducing the loss resistance makes the radiation resistance most of the resistance in the circuit, and that increases the overall efficiency of the antenna. So the more radials, the longer, etc., the less the ground loss is going to be, the more efficient your antenna is going to be overall. So for an HF vertical, there are two different ways to do radials. One is elevated radial. So this is 3 or 4 resonant wires per band you expect to operate. The other way is with ground radials, which are wires 1/4 wavelength or longer for the lowest band. The more the better. There's a diminishing improvement as you add more wires or make them longer, but it is an improvement. Automotive antennas almost all use the metal of the vehicle as a counterpoise. The magnetic ones capacitively couple to the roof of the car. The permanent ones electrically couple through their mount. Mobile antennas need a counterpoise, so if you ever hook up a mobile antenna without a big piece of metal or 4 or 5 quarter wave radials under it, it doesn't work that well. All it's got for a counterpoise is the shield of the coax. At VHF, fiberglass boats generally use vertical dipoles, or the feed line is an unintentional counterpoise. Marine HF gets complicated enough for its own talk. So again, there are two kinds of radials. Resonant radials are cut to a quarter wave for a particular frequency and couple efficiently to the overall circuit of the antenna and space-time at that frequency. They must be elevated from the ground, and I don't mean inches, I mean feet. Unresonant radials work over a broad bandwidth, but they require more material and space, and those are generally on the ground. So let's talk about transmission lines. When you have a current, an AC current going through 2 wires, especially an RF current, it's not as simple as you might think. The wire behaves as a long reactive network, an inductive and capacitive network. This is due to interaction with materials around the wire and with space-time. So this is called a transmission line, and you were expecting to have 2 wires, and in reality it looks like this. Coaxial cable and ladder line are deliberately constructed to be transmission lines and to have a well-defined impedance along their entire length. The original understanding of transmission lines was developed with the electric telegraph. AC power distribution uses transmission lines, and their issues are motivating a switch to long-distance distribution using DC, and also because DC carries 1.4 times as much power as AC for the same voltage. Now, let's talk about velocity factor and propagation speed. The propagation speed through a transmission line is slower than the speed of light in vacuum. It's the speed of oscillating electricity going through that network I showed of inductances and capacitances. This is true for all matter. Matter interacts with light and electricity going through it, slowing it down. And we call this difference in speed the velocity factor. Light travels at 186,282 miles per second in vacuum. Okay, that's in vacuum, not in anything else. Electricity travels more slowly through matter because of its interaction with the matter. The difference is the velocity factor. Bare copper wire in air has a velocity factor of around 0.95. This affects the electrical length of the wire and the size you cut it to match a wavelength. So you will be cutting your radials and antenna wires to about 5% less than the actual wavelength because of the velocity factor. Ground radials will be electrically longer than the same wire in the air, as the effect of the ground is much stronger than the effect of air, and it really reduces the velocity factor of those radials. So an eighth wave radial on the ground may be electrically closer to 1/4 wave. We still want those radials longer to catch as much of the near field as possible. The velocity factor of wires on the ground changes with ground conductivity, and of course that changes with rain. Because we can't count on the electrical length, we just use a lot of radials, and we make them longer. If you've ever made a beverage on ground antenna, that's electrically longer because of this effect. So many VHF and UHF base antennas have radials much smaller than 1/4 wave that might provide an adequate impedance match but a poor current return. Some or most of the current may be returning through the feed line and the mast, making that a vertical dipole, or the vertical element may actually be acting as an end-fed half wave. So here's a place we really skimp on radials. Where's the counterpoise of this HT? It's the PCB, any conductive part of the case, and you, the operator. So we can make tails, wires that are shorter than your height, connected to the shield part of the antenna connector to provide a better counterpoise, and that's useful for improving range. Of course, using something other than a rubber ducky is going to help too. Let's talk about the skin effect. The inductance of a wire forces RF to travel along its skin only, not along the entire wire, only the skin. Common mode return current picked up by your feed line is on the outer skin of the coax, and if you've ever used a clip-on choke, it can stop that current because it has a inductive relationship with the outer skin of the coax. The return of current from the antenna is on the inner skin of the coax. A clip-on choke doesn't affect it. Because of the skin effect, the inner and outer skin of the coax are effectively two separate conductors. Of course, we connect them at the ends. So how does the end-fed half-wave antenna work? A half-wave dipole has maximum current, minimum voltage, and lowest impedance at the center, and maximum voltage, minimum current, and very high, theoretically infinite, impedance at the ends. A half-wave dipole is usually fed from the center and has an impedance of about 72 ohms there. But you can feed a dipole from any point along its length. Okay, you are used to feeding dipoles from the middle. but you don't have to. You can feed it from any point along its length. However, the impedance changes when you do. The radiation pattern of the dipole does not change substantially as you move the feed point, as long as you have a good choker transformer isolating the feed line. If you don't, the feed line radiates and the pattern is distorted. But let's assume you have a good choker transformer. Then even if you feed a dipole from some other place than the center, its radiation pattern does not change substantially. The impedance, however, changes a lot as the feed point moves. At the very end, it's a one-terminal circuit. Of course, you could connect ground or radials, but the feed point would then be between them instead of at the end. So the dipole current distribution is unchanged no matter where the feed point is. So at the left here, I have the feed point in the middle. The dotted lines are showing the voltage. The blue line is showing the current. Okay, now in the center, I've moved the feed point, that's the yellow dot, all the way to the right. Now it has a 200 ohm impedance instead of the 72 ohm impedance I had in the center on this left diagram. So the feed point is off center, but look, the voltage is the same, the current is the same. And now I move it all the way to the right. Well, this is theoretical. It's not physically possible, but I still have the same current and voltage. However, the impedance is around 2,500 ohms. And let's look at this interactively. So here's a program I had the AI make for me, and it's showing an impedance meter and the feed point of a half-wave dipole. So I'm starting out with the feed point in the center. There it is. And as it's in the center, the impedance is 72 ohms. And as I move it to the left, you can see the impedance climb. And as we get closer to the left side, it climbs precipitously. So here's a circuit for an end-fed half-wave antenna, and we have the infamous 0.05 wavelength, so-called counterpoise on the left. We have our matching transformer. You may not have a capacitor in yours there. We have the end-fed half-wavelength antenna on the right. Okay, so most of the wire is on the right, only a very short piece is on the left. So this is a dipole fed very close to one end. The short section is not really a counterpoise, or much of a counterpoise at all. It is mainly a capacitor against ground so that the transformer works. The short and long section together act as a dipole, and thus about half of the long section is the current return for the other half of the long section. So the wire on the right is both the current source and the current sink. Most end-fed half-wave don't have the capacitor shown. They may have a different transformer. So here's the current distribution on the end-fed half-wave. So the box on the left here is our 49-to-1 unum transformer. We have a short counterpoise antenna to the left of that. And then to the right, we have this half-wave wire. And what we're showing is the blue portion here is the current source. And we're showing the current curve of it. It's truncated to fit in the picture. And then we have the middle and then we have the right. And so we have the return portion, same wire. Half of it is returning current, half of it is sourcing current. So that's how an end-fed half wave actually works. Took me a long time to figure out. Antennas on lower bands than the fundamental frequency. Okay, so we've got our end-fed half wave. It's 130 feet long. It's cut for 80 meters. We can use it on higher bands, but now we want to work 160. What's the best way to do that? Short the feed line and use the feed line and the antenna as a T antenna against any counterpoise that you have, or failing that, a ground rod. The feed line becomes part of the antenna. The shack RF may be severe. This is probably a better thing to use in the field. The more counterpoise wires you have on the ground, the better this is going to work. Let's talk about dipoles on higher bands than the fundamental frequency. Well, we have a controversy here because single band dipoles fed at their center have a reasonable impedance on odd harmonics of their fundamental frequency. So an 80-meter dipole doesn't have any useful harmonics on 40, 20, 10, because those are all even harmonics. A 40-meter dipole has a third harmonic at 15 meters. So how do we get around this? The end-fed half wave gets around it. The G5RV also gets around it. The G5RV gets around it because the ladder line feed is part of the antenna on most bands. An off-center fed antenna of the right length can actually have a reasonable impedance on most HF amateur bands. And this is why the end-fed half wave can work well above its fundamental frequency when a dipole would not. A Windham is another example of a multiband off-center fed wire antenna. It's fed 1/3 of the way to one end. So how do we do multiband on a wire antenna? An off-center fed antenna works best with a tuner at the antenna so that there isn't loss on the feed line from the high SWR. The old MFJ remote tuners were good for this. New ones are coming out from other companies. The 130-foot end-fed half wave is resonant on the digital portion of 80 meters. Don't cut it shorter because then it's not resonant on the other bands you want to use it for. And of course we have fan dipoles as well, and fan dipoles have multiple wires per one for each band, and that's how they can work on different bands. So let's talk about an HF vertical antenna and radials on the ground. The importance of this counterpoise is acknowledged by many hams. Okay, so here's a place where they say, yeah, you need a counterpoise. You need it under your HF vertical. There are a number of commercial HF antennas with a tiny counterpoise, and these have questionable results. So what is it about 120 radials? Once in a while, someone will say, well, you need 120 radials half wave long under your vertical. You really don't. In an AM broadcast station site application, okay, so this is not you, it's a commercial radio station, FCC has historically required either 120 radials each half wave long or theoretical modeling of the grounding system. And people just do the radials because they can afford the land and the wire for a commercial station, and it's easy, and then they don't have to submit theoretical modeling to FCC, which will take a long time. And this all originates in a 1937 technical paper and lives, it's getting close to a century later. So 120 half-wave radials is overkill for all but the most zealotly perfectionist of radio amateurs. So if you have that, you can be proud of your zealotly perfectionism. A length of half wave at the lowest expected frequency is considered good for amateur applications, for your radials on the ground. This is still 65 feet for 80 meters and 130 foot square lot. So compromise might be necessary. There is diminishing improvement with additional length, but there's still improvement. As the number of radials increase, there's diminishing improvement, but again, still improvement. 16 is a good minimum. You can feel good about 32. There isn't a limit. In contrast with on-ground radials, 3 or 4 elevated radials cut to resonance for each band you expect to operate are considered efficient. So if you can have the base of your vertical 8 feet high and all your radials coming off from that point, you can do it very efficiently with very few wires. Just keep them elevated along their entire length. So the counterpoise is important. It's as important as the part of the antenna you think of as the radiating element, and it takes part equally in making the radiation. Unfortunately, the counterpoise requires space and work, so it's often ignored to the ham's disadvantage. So let's talk about electrically short antennas, because that's a question I got before I did the talk. So it's often necessary for hams to use electrically short antennas because they can't afford lots of land and, really big antennas. So let's look at their efficiency. And so I've shown 3 compromise antennas. The best antenna is the one that gets you on the air. It beats waiting forever to get the optimum antenna. So some of you are going to go with the compromise antenna. We're going to make clear what the cost is. So what's an optimum antenna? So for this talk, I'm going to consider a DX Commander Signature 18 with a good radial field as the most efficient antenna the average ham could be expected to install. You can do better if you're an extreme ham and you have the money and time. And this has changed over time. It used to be a high tower was the best you could do, but a high tower requires a ton of concrete at the bottom. This doesn't. And it actually does, I think, a better job. So why a vertical as the most efficient? A dipole less than half wavelength above the ground will have its pattern distorted toward the vertical direction, and the towers required for 1/2 wavelength height, well, you might as well use them for a halfway vertical. They'd be larger and more expensive than the vertical and mounted in tons of concrete each. And the radiation angle of a vertical is actually very good. So why not do the vertical instead of the dipole? Well, the dipole is directional and the vertical isn't. That's one good reason. Unless you go with 2 or more verticals, then you can make them directional. But now you're an extreme ham. So why the DX Commander Signature 18? It's less than $1,000, and it comes with the radial wire and the guy rope. It's 93% to full length on 80 meters. It's full length on 10 through 40. Its design is a fan vertical. There are separate wires for each band. There are no traps. It's resonant on all the bands you wire it for. No tuner required. Why the Signature 18? It can be kludged to work with 160 with a horizontal wire. There's no or very little concrete required, depending on the soil and what you can use as an anchor. The pole weight is only 18 pounds. The whole kit is 30 pounds. The low weight makes it easier to install and maintain. Not really easy. You're talking about a 30-pound thing that's 65 feet long. It's still going to require at least 2 people to raise it. And the user gets to decide what bands they wire that antenna for. And if they don't like it, they can take it down and change the wire. It's got issues, though. You must install a good radial field. This antenna is pretty damn useless without a good radial field. It's 60 feet tall with guy wires. It's going to be visually not that nice. Mastrand has thinner, less visible guys. I do camo painting sometimes to blend with trees, etc. Man, I think Mastrand actually is camo guy rope. You can't install this alone. In fact, it takes 2 people to twist the sections together and definitely to raise it. And it's all plastic. The components will die eventually. It's a good idea to paint the mast every few years and replace the shock cords that hold those wires. So what are the alternatives? Okay, so here are the things that you might do if you don't want a DX Commander Signature 18. So one is magnetic loop. It's an easy-to-use portable antenna. I was asked about the Gray Line Performance flagpole. It's got no radials. It mounts in concrete. You put a tuner at the base. If you're going to get this, they have an extension section and an optional whip section. Get them both, because the longer it is, the better it's going to work. The other one, which I actually have one of these, it's not my only antenna, is the N6BT vertical dipole. And it's small and light. It's an easy homer field antenna. It's got no radials. And N6BT knows his stuff, but this is a compromise antenna. And he'll admit that. It's great on 20 and 15 and sort of diminishing as you go to other bands. So antenna efficiency for dipoles and verticals increases with the square of the length, square second power. So a dipole or a vertical half the optimum length for the band is 1/4 as efficient. So here we're starting to get a hint of, well, gee, our flagpole isn't as long as the Signature 18, so it's going to be inefficient on 80 and 40, and it's probably going to be a good antenna on 20 and 15. For loops, it's the 4th power of the area times the number of turns. So a full wave loop is a really good antenna. As it gets smaller, its efficiency diminishes quite rapidly. So we all have these little 3-foot diameter loops. And let's think about how efficient that's going to be. Well, a 1-turn loop, even half the optimum size for the band, is 1/16 as efficient. These have about 5% efficiency. No kidding. Still, lots of people work the world on one. I'm not saying don't get it. It's a good antenna. If you can't have something else, it's a great antenna to go to the field and operate very easily. It's just the fact that, you know, you may start out QRP in the field, and this is making you even more QRP than a wire on a fiberglass kite pole, for example. Um, let's talk about commercial electrically short antennas. So again, they're pretty good on 15 and 20. And how does it change as you go to lower frequency bands? It's about a quarter as good on 40. It's about 1/16th as good on 80. Okay, it's still going to work the world for you, just not as well as an optimum antenna. Don't let this stop you. Get the antenna that will get you on the air as soon as possible. Wires are cheap and easy, even if they're in the trees and not optimum. Get the dream antenna when you can, if you ever can. So we're back to the counterpoise. Any antenna ham is likely to encounter, other than a loop or dipole, will need a counterpoise. Compromise antennas tend to skimp on the counterpoise, in part because buyers think the radiating element is most important. It isn't. And that's the talk. I'm going to put the slides on my website, which is down as I record this, but we'll fix that. And this is how you can reach me. That's actually my cell phone. It won't ring when I'm asleep, don't worry. And my email. Thank you very much. It's been great talking with you.